Swayam Prabha. Digital India. Educated India.
See, what I am going to do, I am going to take topics that you have already studied. Many of you are entering plus 2, right? Entering, yeah, already started. Fortunately, many concepts that I am going to choose are going to come from plus 2, okay? But I can't do much because except thermodynamics, I think everything else is in the plus 2. Kinetics, solid state, electrochem. Okay, electrochemistry is not a new topic, number 1. It is an amalgamation of chemical kinetics, okay, equilibrium thermodynamics and thermodynamics. With these 3, you put and grind, you get electrochemistry. You right, no? Because why I am saying this? Because you should not think electrochemistry as a new subject. If you think like that, you will feel tensed. If you think it is already what is known to you, then it is easier. Okay? So, I am going to do a few things. As I said, the topics that you are going to study in plus 2, I will use here to make this research problem. Okay? So, this research problem you will see only so much, only plus 2 science is needed. Okay? Right. Now, in the solid state chemistry, you might have studied about the FCC lattice, BCC lattice, HCP lattice, no, right. So, that is the problem because some content I am taking from plus 2. So, I will give a brief introduction to what is FCC. From there, I will jump into probably the other topic. Solid state is deleted from the syllabus. But only in the board it is deleted, but it is still there for your JEE. Yes. Yeah. So, I hope many of you will do. Okay, JEE syllabus is different from the board syllabus. Okay, what people do in board, every time there is a suicide, one chapter will be cut. Right? Right, no, that is what they do. Right, no? And how do they cut? They cut mindlessly, they cut. Okay, mindlessly. What is mindless cut? I taught my daughter 9th standard, she is entering, I was teaching her mathematics. So, I think in the polynomials chapter they pulled out some few pages to reduce the burden, but in the exercise section it says it refers to a problem 10.3, but that is in the pulled out portion. Correct? This is called mindless way of reducing subject. If you are serious, you have to review from the line 1 to line n, right. You can't simply remove few pages and say you see book reduced in size. Right. So, this may happen, okay, because people who are in the top what you call the director of education, whatever it is, are not paying so much attention. So, let us not worry about that. Okay. Your JEE syllabus is not truncated, it is as it is. So, you should only prepare for that. Okay. Finally, what happened? I bought new books for my daughter, but I started using my son's book for her. Why? Because in this mindlessly some pages are pulled. It is very difficult for me to teach her. So, I go back to the old book. Okay. Anyway, that jokes apart. Let us now, because since you have not learned, many of you did not, is not familiar with the solid state topic, I will give a little bit of solid state, then go into the battery. Okay. So, let me see whether I have those slides here. If I have, it is easier for me, otherwise it is difficult, because certain things I assumed it is there. Okay. Cubic close packing is there. So, I will start here. Before going to that, something about electrochemistry, because you know at least chemical kinetics, although it is coming in the second year, you know at least the rate equation and so on, right. So, that is enough. Let us start. Now, so suppose a reaction, chemical reaction A goes to B. How do you write rate of the reaction? Rate of the reaction as the rate constant of this process times the concentration of the species power n. If I say it is a first order, power 1, right. So, most of the electrochemical reactions are first order or 0 order. So, I choose only first order reaction here for example. Now, let us substitute the units. What is the unit of K? What is the unit of A, square bracket? Moles per centimeter cube or liter, whatever it is, right? This is the moles per centimeter cube per second, because it is a homogeneous reaction. Homogeneous reaction means the reaction happens in the whole phase, in the whole volume. It does not happen here and there, it is in the whole volume. But what is the difference between the electrochemical reaction and this reaction? Electrochemical reactions always heterogeneous. What is heterogeneous? You have an electrode, and the electrode you put in some solution, and you need minimum of 2 electrode to carry out a reaction. Why you need a 2 electrode to carry out a reaction? Suppose I connect this to a battery to do an electrical work. Okay, the battery, this terminal is called negative terminal, this terminal is called positive terminal. When the battery works, it will eject electron from this terminal. Okay, so and the electron will enter through this terminal, right? So if the electron is ejected through this terminal, this is entering this electrode, then what reaction will happen here? Reduction or oxidation? Reduction. Some reduction reaction will happen here, depending upon what is my electrolytes, reaction will be different. If it is a dilute hydrochloric acid, the reduction is proton reducing to hydrogen. Okay. If it is some other solution, then that particular reduction reaction will happen. So now if I say it is a dilute hydrochloric acid, then you will have one side proton going to hydrogen, the other side chloride going to chlorine. Okay. So this is an oxidation process, this is a reduction process. So we are doing electrical work. If you look at carefully, this particular battery is giving energy, and this is also in a battery kind of, or you can call it as an electrolyzer. This particular system is consuming that energy. Okay. So energy taken from here, invested here. Okay. If something gives energy, we say that particular device is working in galvanic mode. It is called galvanic cell. Okay. Galvanic mode. Galvanic mode means it is giving energy. This particular cell is working in electrolytic mode. That means it takes energy. For example, your cell phone, when you are connected to a wall charger, then it is in electrolytic mode, because it is accepting energy. The battery in your cell phone is in electrolytic mode. When you pull out the cable, start using your cell phone, then the battery gives energy to your electronics, right? Then it is in a galvanic mode, okay, because it is giving energy. Other one is also. So same device can be a galvanic mode or in electrolytic mode. Okay. In thermodynamics terms, work done on the system, work done by the system. When the battery works for you, work done by the system. When the battery takes energy from the wall charger, it is work done on the system, wherein the system is your battery. So you see now, same thing that you have studied in thermodynamics is coming in electrochemistry. Okay. Now in the rate of the reaction in chemical kinetics, we express as moles per second per centimeter. How do you do it in electrochemistry? In electrochemistry, I will rewrite it little differently. I do it like this. Okay. Okay. See, now if I take this electron from this species, and this electron has to go somewhere, there may be something C that takes the electron, gives say C minus. So the overall reaction is A plus C giving AC. Okay. This is a chemical reaction. Here I have decoupled it into two half cell reaction. So here you can see electron. Whenever you see electron, then only it is electrochemical reaction, because that electron will travel through the external circuit. Okay, that electron will travel through the external circuit, right? If the electron does not travel through external circuit, for example, if I mix A and C, the electron need not travel through external circuit. Electron will go from A to C directly. That is a chemical reaction. If you let the electron, say A oxidizes here to A plus, and the electron goes like this, comes this side, then C takes that electron, becomes C minus. Then you produce AC in the solution. What did I say? If C who is ejecting electron? If A eject electron, becomes A plus plus electron, that electron goes through this, and the electron comes here. Here the C consumes that electron, produces C minus. You see, this is electrochemical reaction. The product is same in chemical as well as in electrochemical. Only thing is, we let that electron pass through the circuit Why do we do that? Then only we can do electrical work. Otherwise, it will be a chemical work. In chemical work, what you get? You get heat. Here, instead of heat, I am producing electricity. Okay, again is thermodynamics. One form of energy can be converted into another form of energy, but you can't destroy it or make it. New energy, you cannot make it. Same here. Here, the chemical energy is converted into electrical energy. For that, you need a device called electrochemical cell. The electrochemical cells can operate in galvanic mode or in electrolytic mode, depending upon how do you set up. Okay, how do you set up means in your books, wherever delta G is negative, all those reactions I can set it up in galvanic mode. Delta G negative, spontaneous, right? All spontaneous reaction, what happened? Delta G less than 0 negative is spontaneous reaction according to thermodynamics. All those spontaneous reaction I can convert into an electrochemical cell. What kind of electrochemical cell? Galvanic cell. It will give energy. Wherever delta G is positive, again I can convert into a cell. It will become an electrolytic cell. For example, if I have hydrogen and hydrogen can get oxidized, produce 2 electron, and you have oxygen which takes up this 2 electron, produce oxide, net reaction is this. Okay. This is your net reaction. Depending upon the temperature, water can be liquid or it can be in vapor phase, right? Clear? For this reaction in standard condition, delta G is negative. Correct or not? In your textbook, you go check it. Delta G for this reaction is negative. You can calculate corresponding E naught value. For calculating E naught value, you have to use this relation. Correct? Oh, sorry. Opposite. Right? You can use this relation. You see, if delta G is negative, then E cell has to be positive because N is a number, F is a number. Okay, they are positive numbers. So, if delta G is negative, then E cell has to be positive. If E cell is positive, such cells will be galvanic cells. Okay, what is happening? I am oxidizing in one side hydrogen, in the other side I am reducing oxygen. I am routing the electron to the external circuit, getting the electrical energy done. So, in this process you get plus electrical energy. Of course, some heat will be there because you have an IR drop in the system, but that will be very minimal. Okay. So, this is what going to happen, but you see fuel cell works, we have seen fuel cell bus, but you take hydrogen in a balloon, open it here, let it go out, you do not see the hydrogen reacting with oxygen, it does not produce water. You take hydrogen cylinder, open it, it does not produce water, whereas fuel cell works, same reaction. What is the magic? So that is where the kinetics comes. The activation energy for the reaction, if it is very high, that it cannot be supplied in the conditions in which you have taken the reactant, you know the collision theory. Particles has to collide. It has to collide with sufficient kinetic energy. It has to collide with sufficient kinetic energy plus right orientation. Then you have reaction. Simply by collision, whatever may be the energy, reaction will not happen. Orientation is important. Okay, hydrogen's 1s orbital, hydrogen molecule, it is going to be a molecular orbital, okay, sigma 1s. So, sigma 1s molecular orbital of your hydrogen and your oxygen's O2's molecular orbital, these two guys should interact in particular orientation. What is the probability that they interact in that orientation? They collide. They may collide with sufficient kinetic energy, they may not collide in the right orientation. Therefore, electron cannot be moved from hydrogen to oxygen. We call that, physical chemists call that a high activation process. Okay, because I am not able to transfer the electron, there is no way, because the orientation always, very rarely they come in right orientation. That means, we take hydrogen plus oxygen, put it in a container, leave it for infinite years and then come back and see, you may find water. Because slowly reaction happen in infinite years, everything reacted. But we will not be there infinite years to see that. Who will verify that fact? Okay. So, what we do then? We put catalyst. In hydrogen oxygen fuel cell, we take platinum as a catalyst. On platinum, the hydrogen when it comes and hits the platinum, it will stick. Why it will stick? Again same concept. The d orbitals of platinum will overlap with the sigma 1s orbital of hydrogen, and it will form a hybridization, that is nothing but bonding. So, hydrogen can adsorb, it is called chemisorb. What is chemisorption? What is the difference between the chemisorption and physisorption? Physisorption is mostly van der Waals force. Chemisorption is a bonding. If hydrogen comes and hits the platinum, it will form a bonding. It will form a platinum and hydrogen bond will form. Okay. So, that is a kind of chemisorption. Same oxygen when it goes to hit platinum, it will form a bond. But when the hydrogen and oxygen, since they are able to bind with the platinum, now we can oxidize hydrogen because it is under the control of platinum. So, platinum now can oxidize hydrogen, it can reduce oxygen. So, the fuel cell reaction is feasible with a catalyst. Basically, catalyst helps to reduce the activation energy, giving an alternative path. In other words, catalyst helps to reach the equilibrium point faster. Okay, that is what it is doing. Since it is able to reach the equilibrium point faster, delta G is negative, we can verify for this reaction using a catalyst. But if you want to verify for this reaction delta G negative or not, it will take infinite years. But if the catalyst, you can verify that fact, right. So, you need a catalyst in fuel cell, that is the platinum mostly, platinum alloys or platinum catalyst, which we use and then do the reaction, very simple. So, now you understood, yeah.
So, why only platinum, not any other heavy metal?
Yes, as I told you, answer is in the collision theory only.
Which has empty d orbital.
Yes, it has to have a right energy. You understood? You cannot couple two things whose energy lies very different in space. You cannot move the electron. The electron has to move from one orbital to another orbital. Their energies should be comparable. Then only you will have overlap. It is too abstract in plus 2 textbook. There is a quantum chemistry portion. The quantum chemistry, they discuss about the orbitals, nodes and things like that. But if you little good higher level quantum chemistry, if you go, they will talk something called overlap integral. What is overlap integral? We have for each orbital, we have a wave function, right? You have a wave function. And how do you find the probability of finding the electron? You have to square the wave function. Suppose I have two different orbital, okay, there are two different orbital. Suppose psi 1s, okay, and in case of platinum it is psi 3d, okay, this is a platinum case, this is hydrogen case. So, you do this integral, d tau is the volume element, okay, dx, dy, dz. So, if you do this integral within the limits where the 3d orbital and s orbital lies, okay, if we do this integral, it will return a value. If that value is some constant, what is that constant is called? This is called overlap integral. That magnitude of that constant tells you how much overlap happens. Okay. If the overlap is very strong, that overlap integral value will be maximum. That means bonding is possible. Okay. Otherwise, bonding, if that integral returns a value of 0, it means there is no bonding. We call it as anti-bonding. Okay. It will result only anti-bonding kind of a scenario. If you mix two orbitals, it will form one bonding, one anti-bonding. Anti-bonding will be higher energy, bonding will be lower energy. There won't be any overlap in anti-bonding. In bonding, you will have a good overlap. Electrons will freely move from this orbital to the other orbital and so on. Okay. These things we don't recur now. I am just giving you a concept. Okay. So, now let us look at this problem. If delta G is negative, this is a galvanic process, right? It will give energy to you. So, in some reactions where thermodynamics says it is delta G is negative, but you may not see it is happening, for that you need to put the catalyst, then it will happen. Okay. Now, you see inherently the fuel cell reaction or battery reactions are heterogeneous in nature. Why? Because you have an electrode, platinum electrode, and the hydrogen comes and gets oxidized to proton, correct, leaving the electron in the metal. This fellow is in gaseous phase, electrode is in solid phase. Similarly, if you go here, these species were in the liquid phase and the electrode is in the solid phase. So, where the reaction happens? Reaction happens at the interface of these two phases, solid phase, which is your electrode, and the liquid phase where your reactants are there, or gaseous phase also reactants can be there like in fuel cell. So, at the interface only reaction happens. Whereas in the regular chemical kinetics, if it is a gaseous phase reaction or liquid phase reaction happens in the entire bulk. Every volume element in the trough, you go and check it, you will see the reaction happening to the same extent. Whereas here, you go check whether reaction happens here or not, it will not happen. Only on the surface reaction will be happening. So, it is a heterogeneous, two different phases are involved. In heterogeneous reaction, the rate constant is K is centimeter per second, not second inverse, centimeter per second. Then what will be the unit of this? Mole per centimeter cube, correct? Then it is going to be mole per second per centimeter square.
Area.
Yeah, that is the interfacial area. Area of cross section where the reaction happens, right? So, what is the unit of rate of a reaction in case of heterogeneous reaction? Moles per second per centimeter square. How many moles are converted from reactant to product in 1 unit time in 1 unit area, per unit area, right? That is what the rate of reaction. Just like water, what is the flow rate of water? You know the cross section of the pipe, how many ml of liquid flows every second through 1 unit area of the cross section of the pipe, correct? So, that is liters per second per centimeter square. Okay. Here it is moles per second per centimeter square, same, right? The rate is always will have a inverse of time in it, right? Now, clear, no? So, now what happens? We need to convert that into something which electrochemistry use. I told you electrochemistry is not a new subject, it is an amalgamation of what all you read so far. So, what we got? Rate of the reaction as mole per second per centimeter square. Now, let us take this, let us take 1 mole of hydrogen, oxidize it, it produces 2 moles of proton, 2 moles of electron, correct? Let us look at that reaction. Then what I am going to do? I am going to multiply this, okay? I am getting how many moles of electron? 2 moles of electron. So, N is the number of electron you produce in the reaction, okay? And then I multiply by F is the Faraday constant. What is Faraday constant? Coulombs per mole of electron, coulomb per mole of electron. How much is that? 96,500 coulomb per mole of electron, okay? How much is this? 96,500 roughly coulomb per mole of electron, okay? NF, rate of the reaction, rate. Now, let us look at the unit of this. N has a number, forget about it. Faraday has a unit of coulombs per mole, multiply by rate has a unit of mole per second per. So, now cancel. What is coulomb per second? So, if kinetic chemists talk about rate of the reaction, electrochemists talk about current or current density. Why current density? Ampere per unit area is current density. If it is in the unit of ampere, it is current. Yeah, if it is in the unit of ampere, it is current. If it is a unit of ampere per centimeter square, it is current density. How does it different? Suppose I have a 5 centimeter square sized electrode, then I need to multiply this by 5 centimeter square in order to get what is the total current of the system. If I have a 10 centimeter square electrode, you multiply with that number with the 10, you get what is the total current that is coming out of the system. Am I right? So, wherever you talk about rate of the reaction in chemistry, electrochemist will talk current of the reaction or current density of the reaction. Okay? And already we have done this one. Wherever we talk about delta G naught, electrochemist will talk about E cell naught. So, delta G becomes E, rate of the reaction becomes current density.
NF rate is known as current density, sir?
Yes.
Or some other name is also?
That is all, current density. See, it comes out the unit of current density, there is no other name, right. So, now we have understood how do we convert a rate of the reaction to current density, how do we convert a delta G of the reaction to cell voltage. Only these two we need to do that. Okay. Now, let us look at this.
what is E naught cell?
Okay. See, if you go to the second year, you will see something called standard reduction potential. How does it develops? Let us take this. We take a zinc rod and dip it in the zinc sulfate solution. Okay, zinc sulfate solution. I use this also as an energy axis. It's a energy axis. Okay. Now I will take a copper rod dipped in, say, copper sulfate solution. Okay. Let us take methane. What is the coordination number of carbon in methane? 4. Why so much thinking? The sleep also, if I wake up, you should tell it is 4. Only 4 hydrogen is attached. Right. Now, let us take zinc. Let us take zinc, or let me take say platinum, because that is known, probably in your textbook it is there. Platinum is in FCC unit cell. Okay. So, FCC unit cell means you have atoms like this. Okay. One platinum particle is in contact with 6 platinum particle, and then you have particle here. Okay. Then 3 particle above that layer. Similarly, just below this 3 particles below that layer. That means the center particle is in touch with something like 12 particles are there. So, I will say it is a coordination number 12, because one particle is in touch with 12 other atoms equidistant from it, right. So, you see, now imagine you take a platinum ingot. What about the coordination number of platinum right on the surface?
That would be 9.
Correct. So, it is missing 3, and I cut it in the side also, then what will happen?
Again 6.
Wow, if I cut it here, it is losing another 3, correct, no? So, that means cutting means I make like a very sharp tip. Okay, it loses its neighbors in all direction. As it loses neighbor, it is less in coordination number, right, surrounded by atoms, right, less number of atoms are. What will happen? See, every atom, one atom is bound to another atom by a bond, chemical bond is there, which is binding these two guys. If you are removing an atom, means you are breaking the bond. When you break the bond, each bond has 2 electrons. Either both the electron go to the atom which is leaving, or both the electron can stay back with the atom which is there in the material, or one this will take, one the other one will take. Homolytic or heterolytic cleavage can happen, correct. So, in any case, your surface will be either charged or radicals will be there, correct. Now, once you have radicals on the surface or charged, it will not keep quiet, it will always try to find a neighbor, so that its coordination number is reached, right, it forms a coordination. That means, it is willing to make a chemical reaction with some species in the surrounding. Now, I have taken zinc, same situation, the zinc atom in the surface will have less coordination number. This guy is willing to make a bond with its surrounding. Similarly, I have a copper, the copper fellow will have less coordination number on the surface. It will also want to make a bond with the surrounding. What I have is aqueous solution of copper sulfate there, aqueous solution of zinc sulfate there. Okay. Imagine if the Fermi level, you know what is Fermi level? There is no value for that. What is the Fermi level for a metal? It is the Fermi level. In physics, it you have studied or not? It is the topmost level, the topmost filled level. Okay, in a metal. Okay, electrons you are populating, right. So, in a solid state, you forms a band. We have a valency band, conduction band. So, if it is a metal, mostly either the band will be off filled, or maybe valency band and conduction band may be overlapping, so that the resultant band becomes partly filled. Okay. So, you have a band which is partly filled. The topmost point of that band which is partly filled is called Fermi level. Okay. That is where the electron, the highest energy electron is living. Okay. So, you have a Fermi level say somewhere here, because I am using this as an axis also. So, do not think that Fermi level in a zinc metal will be here, no, this is zinc metal, I agree, but I am using this also as an axis. So, I am just arbitrarily saying this is the Fermi level of this entire zinc plate, okay. This is EF. Okay. Now, say the Fermi level in case of liquid 1 molar zinc sulfate, because here which is a reactive element, reactive species is a zinc. Zinc 2 plus is a reactive species here. Other than that, you have is a water, so you have proton also is one of the reactive species here from the water. Okay. Now, this energy level somewhere here, let us say. Okay. So, you have or let me put this is a some sort of molecular orbital of a species in the solution which likes to receive the electron. It is some sort of a empty molecular orbital, you know it is LUMO, lowest unoccupied molecular orbital of a species. You know what is LUMO, lowest unoccupied molecular orbital? So, you know sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, okay, and then pi 2p. Okay. Suppose you have electrons filled all these fellows and here no electron, okay, that will be the lowest unoccupied level. Okay. So, that is the empty level where you can further add the electron. Okay. So, now you see this fellow is a lowest unoccupied molecular orbital of some reactive species in the solution. Now, if you put these two together, what will happen? Here electron is at a higher energy, here there is an orbital which does not have electron, then the electron might jump from here to here, nothing but there will be a reaction between these two fellows. Okay. If electron jumps from here to here, okay, the situation I have taken is slightly different. So, I will put this zinc sulfate solution is here, okay, and in this case I will put a Fermi level here and here I will put the solution. Okay. There is a reason why I did it, because I have chosen particular concentration. So, it will be like that. Okay. Now, let us take in this case. So, this you have a LUMO here for some species which is undergoing reduction here, and this is the Fermi level. Then what will happen? The electron from here will jump here. If electron jumps here, this level will rise because some species in the solution getting reduced. Okay, the composition of the solution is changing. If the composition is changing, chemical potential of the solution will change. Okay. Now, this fellow will drop in its level because it is losing electron. There is a receding of electron there, right. Somewhere after some time it will reach an equilibrium. Okay. When it reaches equilibrium, these two levels will be equal. Now, by the time it reaches equilibrium, it is like your semiconductor physics, p-n junction. What happens in p-n junction? You have a space charge layer generated. Why? Because the electron moves from one phase to another phase, okay, and then it creates a space charge layer. Same here. Here it moved from this phase to this phase. Then here you will have more positive charge. Why? Because electron is lost. So, this you can say some species underwent reduction, some negative species is generated. So, you will have equivalent amount of negative charge here, correct. So, here you have positive charge, here you have negative charge, am I right? So, you have a charge separation. Anywhere in the solution you go, there won't be any charge separation. Equal number of anion and cation you will find if they are divalent, right. Equal number of anion and cation you find here. But you see in this region, it will be some few nanometer thick. Okay. In this region, you see there is a space charge layer. There is a positive charge in one side, there is a negative charge in the other side. We call it as a double layer. There are two layers, one positive layer, one negative layer. So, this double layer causes the development of potential. Somebody asked you what is E naught, that E naught is that the potential that is generated because of this reaction. This is also called galvanic potential. Okay. This is customary electrical science, we take the positive charge is higher in potential, negative is lower in potential, so we write it like this. Okay. So, this is the potential drop across this interface, which is a result of a chemical reaction. What is that chemical reaction? It is an attempt to make these levels of your solution and the electrode to be at par, there is an equilibration. How much you need to do that? It is only few nanomole or much lower than that is what needed. You will not think reaction will be continuously happening, no, very small amount of charge you need, some microfarad or picofarad kind of I mean not Farad, microcoulomb or picocoulomb kind of a small amount of charge only need to be passed, by then it will establish this layer. Okay. Some interfaces will quickly reach this level, some interfaces will quickly reach this equilibrium level, some will go very slowly. That means even for this reaction there is an activation barrier, correct, no? Those interfaces or electrode electrolyte combination which reaches this equilibrium potential very quickly will be used as reference electrode. Reference electrode, like standard hydrogen electrode you will study, wherein you take a platinum electrode and you will have hydrochloric acid in which you bubble hydrogen gas at 1 atmospheric pressure. What is the reaction there? Hydrogen is adsorbing on the platinum, so it will be an equilibrium between the hydrogen, the gas phase, liquid phase and the platinum, right. So, again there is a reaction, so there is an equilibration, right. So, those interfaces which will quickly form, we will use as a reference electrode, because whose potential will quickly form, you can use that as a reference to measure some other cell's potential. Okay. So, those interfaces which takes time cannot be used as a reference electrode. So, there will be a question, why always specific electrodes are used as a reference electrode, that is the reason, correct, no. Now, look at here, in this case the energy level of liquid side is higher than the Fermi level. Now, to equilibrate, if I say that is a high impedance process, high activation energy process, huh? Yes, more, but if I say that electron jumping, see you in the chemical kinetics you have reactant here, product here, then reactant should become product, it goes like that. Similarly, here there is issues, it will not go, here it is not going, I am saying, then what is the way? No, what will become thin? No, I have taken a large electrode and dipped, very flat electrode I dipped, there is no shape change, nothing. See, there is one more way. If zinc oxidizes, gets into the solution, leaving back the electron here, then also it can rise, right. So, this will come down because you are adding positive charge, this will rise up because you are leaving behind the electron there. Okay. When you combine zinc to copper electrode, zinc electrode is called as a negative electrode. Why negative electrode? Because this carries negative charge. Okay. Zinc is a negative electrode where oxidation happens, zinc is oxidizing here. Okay. Copper is a positive electrode because copper itself is positively charged when you put in the solution. So, again same thing, here electron is added, so this level rises, this level drops, then you will have an equilibration. Again there is a electron here, positive charge here, there will be a potential drop across this interface, double layer. So, this is the origin of E naught of this electrode, E naught of that electrode. What is E naught cell? E naught cell is a E naught of cathode minus E naught of anode. E naught value of cathode versus E naught value of anode, that is your E naught cell. Clear, no? Any doubt in that? The problem here is, how do I measure what is this potential drop? To measure what is this potential drop, only device I have is a voltmeter, but voltmeter needs 2 terminal. You need to use a reference electrode. Therein we will use standard hydrogen electrode. In standard hydrogen electrode also we have a potential drop, but we will not worry about that. We will say that drop is 0. So, with respect to that, how much is the value of zinc electrode, with respect to that how much is the value of copper electrode, we can measure. Am I right? It is like this. E cell is what is the potential of your cathode with respect to the potential of standard hydrogen electrode, and what is the potential of your anode with respect to the potential of standard hydrogen electrode. Okay. Now, this will reduce to E cathode minus E anode. Am I right? What I have done? I have done 2 measurements here. What is the first measurement? In the first measurement, I have measured the potential of my cathode with respect to a reference electrode. In the second measurement, I measured the potential of my anode with respect to a reference electrode. In both the cases, I used same reference electrode, So, the difference you see the reference electrode will vanish. It is nothing but the difference in potential of these two electrodes. Obviously, when you have a zinc and copper, you have got already two terminal, you can directly connect and measure. Why do you need a reference electrode here? Correct, no? But the problem is this difference is say 1 volt. This 1 volt can be produced by combination of two values of anything. You will not know exactly what was the anode value, exactly what was cathode value. You all know the difference is 1. Was it 3, 2 or 1, 2 or minus 2, whatever it is, or it is 4, 3 or 5, 4 or 6, 5, all of them will give a difference of 1. Only thing is, if you directly take a voltmeter, connect to zinc and copper, you will get the voltage, but you do not know what was the voltage of zinc, what was the voltage of copper. But if you go through this method, you will know what was the voltage of zinc, what was the voltage of copper, and those are the values in standard condition listed in the table. That is called electrochemical series, that will come in your second year. Any questions so far? Any question? No question? Actually, I made a content thinking that you are all plus 2 students. No, you are entering plus 2. So, I cannot go over all the content which I made for you. So, I started teaching on board. Okay. So, yeah, any question? So, now you know what is current, nothing but rate of the reaction. You know what is potential, nothing but delta G. And you know how to measure individual electrode potential using a reference electrode. And you know what is a reference electrode? Electrode which reaches equilibrium faster. Okay, and it should be reproducible also. Okay, tomorrow if somebody does something else, should not come. It should be same, reproducible, right? So, and the standard hydrogen electrode potential, it has some potential drop, but we consider it as 0. We assign a value to it, with respect to that we measure. All of you clear? Now, what we do, suppose I have two reservoirs of water. In one I have water up to here, in another I have water up to here. I somehow connect this, okay. Okay. Now, this is my ground, that means from the ground I have a building, above building I have tanks, okay. Now, if I want to know what is the level of this water, I can either measure from the ground or I can measure from here. If I measure from this to this level, then I should tell my reference is this. If I tell from here, then I should tell my reference is this. So, if you look at that example I have given, the standard hydrogen electrode is like this. This is cathode and anode. You can measure this height, you can measure this height and subtract, that will tell you this height. Clear, no? So, it is like that. Now, you see now, water will flow from here to here automatically. Why? Because this is at higher potential energy than this. It is a natural flow. That is a galvanic cell. Why? If you somehow connect some kind of what do you call that generator here and let the water go through that generator, then you will produce electricity. Potential energy will be converted into electric energy. Okay? But the reverse, in the reverse direction, you have to put energy for the motor to pull the water from here to here or here to here. Correct, no? That is a electrolytic mode, or where you spend energy. Okay? Where you spend energy, we can call it also as energy storage. What I have done, I have taken electricity, used that electricity, took the water from the ground, put it in the overhead tank. By this way, I have stored energy. How did I store energy? Because I changed the potential energy of the same water from some low value to the high value. This is called energy storage. And this is what being performed in pumped hydro units. In pumped hydro, what we do? We take water from a lower reservoir, we pump it to a higher reservoir. Whenever we want electricity, the water from the higher reservoir will be run through a generator, you get electricity. Naturally there are hydro plant. What is natural hydro plant? Whenever there is a river, wherever you find a river and you have a kind of a falls, that region you put this, right, generate electricity. That is naturally produced, wherein energy is spent by the sun to evaporate water, it goes to the clouds, rains, go to the reservoir, comes here, that time we harvest energy. Clear or not? Whereas man-made one are like this. In man-made one, near river we will go, when the river water comes down, we produce electricity. After that, that water will not let go. We will lock it, take a pump, put it back there. You will ask me, why are you doing that? Right? Why do we do that? We do that in future when we have excess energy. For example, now we are going for a wind and solar. Solar will be there only when there is a sun out there. Wind, whenever wind blows only you have wind energy. Suppose in the night I want AC, but neither sun is there nor wind is there. How do you get energy? So the storage is this. Use the energy which is harvested in the daytime, part of it, to put the water from the ground floor to the top floor. In the night you run the water down, you produce electricity, and that electricity will be used for running your AC in the night. This is called energy storage or energy arbitrage.
Sir, exactly how efficient is this method?
So always what you put and what you get will be less than what you put. Okay, it will be about 93% efficient. Pumped hydros, roughly. Okay, so but batteries also again some efficiency are there. So always you lose some energy as heat in this process, but you can't do anything. Because you want energy in the night, you pay for even including wastage. Correct? No, your electricity bill will be based on how many units of electricity used to pump the water, not based on how many units of electricity generated during rundown. So you pay already for the wastage also. Am I right? Clear now? So now what we do is we go back and where is that? Oh, I think I have to go here. Very fast. Okay. Okay. Now, since there is not enough time, I am going to touch your solid state chemistry and close with the battery chemistry. Okay. So now you see here, you have a layer of red atoms, right? I consider that as a layer. A layer means a name given for a layer. And there is another layer which is not exactly on top of the previous layer, which is placed at the voids generated in the previous layer, again following a pattern. So the distance from this to this must be same as this to this. So the pattern should be followed. Now you see I put it here, 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 here. So this I call it as a B layer. Now I can put a third layer. In third layer I have two choices. I can put the third layer here. That means it will be a distinct layer from both A and B, or I can put right here, then it is same as A. So I can form either ABA or ABC and then again A, correct? ABA or ABC, ABC, ABC. If I form ABC, that is called CCP lattice. It is called cubic close packed structure or face centered cubic structure. FCC or CCP both are same. Cubic close packing or face centered cubic lattice, FCC. Okay. So now you make an FCC lattice that will look like this, because there are three different colors I used, and I have connected the atoms such that you see there is a face centered cubic emerge out of there. What is face centered cubic? Face centered cubic means this is my cubical box. If I put atoms in the corner, also in the face centers, okay, then it is called face centered cubic lattice. So if you put atoms A, B, C and you tilt them and then you connect and see, you will see a face center here, right? There is a 4 atoms and 1 atom in the middle, that is a face center. Face center, if you look from the top view, then you will see like this. The top view will be like this, correct? From the top, if you view, it is a phase center. Okay, you see one kind of atom here, another kind of atom, another kind of atom. It's like a layer of 3 different atoms, right? You see that here, 3 different colors. Okay, so the phase centered lattice. Now let us look at this. This is the same thing I have plotted here, except that for clarity, the corner atoms I shrunk. I have shrunk the corner atoms. Remaining phase center atoms I left it as such, so that you can appreciate phase centered cubic lattice. Now what is important? This is a unit cell. Let us assume it is a unit cell, because the same cell is repeating in 3D, forming a big lattice. Then what is the sharing of this atom? How many unit cells share that atom in the phase center? How many unit cells? Yeah, you take a box, stack one over the other. The face of the back shared by how many box? Face of the box shared by how many box? 2. Boundary is same for both the box. Okay, in the real box the boundaries are different, but here it is a 3D lattice. You cannot put one atom over another atom, so it will be one atom in the interface, right? So now you see you have the center, the phase center one shared by 2 lattice. So the contribution for the given unit cell is only half, right? So there are 6 such atoms, 6 into half becomes 3. So 3 atoms which are in the phase center position are belong to the given unit cell. Am I right? What about corner? 1/8. Everybody agree?
Yes.
Because there will be 4 cubes at the bottom. On top of that you can put 4 more cubes. So the center atom in the corner will be shared by all these 8 cubes. Therefore 1/8. There are 8 atoms. 1/8 into 8 is 1. So you get 3 from the phase centers, 1 from the corners. Totally 4 atoms belong to this unit cell. 4 atoms belong to this unit cell. Am I right? Now let us look at different angles. You see there is a cavity produced in the middle. Okay, is there a cavity? The way I have drawn, yes, there is a cavity, because it is not the balls which are touching each other, they are balls which are faced from each other. That will be the real solid. Okay, so if you see there is a cavity, that cavity has got 6 vertices. If I connect all those 6 atoms together, if I connect all the 6 atoms together, it will be like this. Correct? It will form a shape of octahedron. Okay. So what is happening? Octahedron, how many triangular faces are there? That is why it is called octahedron. Octa means 8. There are 8 triangular faces you take, make a closed shape. That is called octahedron. And the center of the octahedron is empty right now. That is called interstitial site, or it is called as a void. So you have a void in the structure. In principle, in the void you can put something which fits there. That is all about lithium ion battery. If you can put a lithium in the void and fit there, then it is a lithium ion battery electrode. Okay. So quickly we will do it, you will see. Now look at the carefully, this is void. Where are the similar voids? Here in the edge center. In the edge center here, edge center there, edge center here, 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 here. How many edge centers are there? How many edge centers are there? 12 are there. What is the sharing of that void? Sharing of this void is 1/4. So 3. So 3 octahedral voids plus in the center one, 4 octahedral voids belong to that unit cell. So let us combine the former and the latter statement. Former I said 4 atoms belong to this unit cell. Now I am saying 4 voids belong to this unit cell. So I rephrase it. If a lattice is made of 4 n atoms, then it will create 4 n octahedral voids. If it is a CCP arrangement or phase centered cubic arrangement, if you take 4 n atoms and make a CCP arrangement, then I will create 4 n octahedral voids. Make sense, no? True, right? Because I took 4 atoms formed 4 whites, 4n atoms will form 4n whites. Yeah. Now let us look at the different, all other atoms which we are not interested, I diminish. Only you look at this atom, one corner atom, 3 face center atoms, you connect them, what shape you get? What you get? How many triangle faces are there? 4. That is why it is tetra. In the center of that also there is a void, right? Not exactly center, it will be close to the base because of the this thing. You see, it will be here. So, likewise, how many tetrahedral voids are there? See, the tetrahedral void is inside the unit cell. You appreciate that? This void is inside the unit cell because this corner atom is taken, these 3 atoms are in the face center. So, this middle portion of this lies inside the unit cell. So, this wholly belong to that. How many such tetrahedral voids are there? 8. 4 facing upward, 4 facing downward, right? From each corner, one this thing will be. So, I rephrase my statement. If I have a FCC lattice made of 4n atoms, I get 4n octahedral voids, 8n tetrahedral voids. Make sense? Agree all of you? So, in a FCC unit cell, if somebody asks you to define FCC unit cell is an arrangement of atoms wherein if n atoms are taken, n octahedral voids will be there and 2n tetrahedral voids will be there. If you make such a unit cell, that is FCC. Am I right? Now, you look at this animation. What I have done, I have shown the octahedra here, okay, and I am showing the tetrahedra, building the tetrahedra around the octahedra. Okay. Now, when you put all the 8 tetrahedra, your octahedra is not seen. It is inside those tetrahedras which are enclosed by these tetrahedras, 8 tetrahedras. Clear? Now, you see again. Okay. See, I have chosen 6 atoms formed octahedra. Now, you see tetrahedra will come. How it will come? Take this atom, connect these 3. Okay. See, started coming. Now, you see octahedra inside, right, like a shadow. You see now, this is the shape. You see octahedra inside. Clear? So, now let us go to the actual thing. Lithium ion battery, you have lithiated graphite as anode, and then you have Li 1 minus X COO2 or lithium cobalt oxide as cathode. Okay, lithium cobalt oxide as cathode. Before explaining what is lithium cobalt oxide structure, let me explain you what is sodium chloride structure. What is sodium chloride structure? See, I have taught you CCP, right? I have taught you CCP. Using CCP definition, you have to explain what is sodium chloride structure. Anybody?
Chloride ions are located at the CCP structures and Na ions are located in the voids.
Which void?
And
No. See, you have to look at the stoichiometry. You have 1 Cl minus, 1 Na plus. You don't have for every Cl minus 2 Na plus. Then you should go to stoichiometry you have to match, na? Now, what is the definition? Why we do that way? Chloride ion is bigger than the Na plus ion. There is a cation, there is an anion. Okay. So, chloride ions, assume chloride ions make the CCP lattice or FCC lattice. Chloride ions make the FCC lattice, and the octahedral voids are occupied by Na plus ion. Octahedral voids are occupied by Na plus ion. That structure is sodium chloride structure. I can put it the other way. Imagine Na plus ion forms a CCP lattice and voids are occupied by chloride ions. That also will form NaCl structure. But we do not consider that way because we know the voids will be limited space. We wanted to put cation there rather than the anion. But mathematically both will give the same structure. Either way you can define. But if you define it in the former way, then you will be considered chemist. If you define it in a later way, you will be considered like a mathematician. I just want to imagine something, that is all. No physical attribute to that. Yeah? Any question so far? Another 5 minutes I am going to wrap up. Yeah? So, now let us take sodium chloride, which is nothing but the FCC lattice of chloride ion. Octahedral voids are filled with Na plus ion. Now, let us write 2 NaCl as Na2Cl2. Na2Cl2. Now, this chloride ions I replace with an oxide ion, and sodium ions I split into 2. One of the sodium ion replaced with lithium, one of the next sodium ion replaced with cobalt, that is LiCO2, lithium cobalt oxide. That is your battery material. How do you define this now? LiCO2 is made of a FCC lattice of oxide ion, wherein half of the octahedral voids are occupied by a lithium plus. Yeah, half means what? One side of the solid will be lithium, one side fully sodium. Huh? So, alternative octahedral voids are occupied by lithium and sodium alternatively, right? Or octahedral voids are occupied by lithium and sodium alternatively. Lithium and cobalt alternatively, right? So, if you do it that way, you get the structure of LiCO2. Then how that structure will look? It will look like this. You see here, these fellows are oxide ions, all phase center, everything fine, and the edge center is octahedral void. Remember, center also octahedral void. So, now what I have done? I have put here cobalt, I have put here and all lithium. So, a layer of lithium oxide, layer of cobalt oxide, lithium oxide. This is called layered material, layered structure. So, lithium cobalt oxide exhibit a layered structure. Where are the layers there? A lithium layer and a cobalt layer. What are the layers there? A lithium layer and cobalt layer. Since lithium is one layer, I can nicely pull that out and then insert lithium again, because there is a way by which I can pull out and put in. Okay? But if you want to enter an octahedral void, you have to go through a tetrahedral void, because the tetrahedras are surrounding the octahedra. Correct, no? That means when you are pushing a lithium ion inside, it has to go through the triangle of your tetrahedral void and then enter into the octahedral void. Correct, no? So, that means the triangular void, triangular face in a tetrahedral void is very small. So, the lithium goes in, all the 3 ions, oxide ions which are there will be repelling that fellow, because electron repulsion will be there. Overcoming that, it has to go. That means lithium will not freely moving in. It has to spend some energy and moving in. That is why while charging the battery, you spend energy. What for you are spending that energy? You are spending this energy to push this lithium into the lattice. Lithium into the lattice. What lithium is doing? He goes to the triangular window and he dilates those oxide ions, and then he gets into first tetrahedral void. From there, he drops down into the octahedral void. Likewise, continuously lithium going in until the entire structure is occupied. So, this needs energy. Therefore, you are spending electricity. When you take it back, again same problem. When it comes also, it has to dilate and come. So, it will spend little bit energy while doing this, and then it will come out. Okay? So, you will indefinitely, invariably you will have some energy loss in this process, but that will be minuscule compared to the total amount of energy you store. Therefore, we can use it as a battery material. Clear? Any question on this?
Sir, we're keeping half of the lithium in the octahedral and the alternate you said, but here we are keeping in the tetrahedral position.
Where you are keeping tetrahedra? Tetrahedra is inside the unit cell. I am keeping at the edge center.
Which is octahedral again.
You remember? Go back. These are all octahedra, right? Edge center is octahedra. This is inside. Am I right? Okay. Now, one last thing. We generally use solid state chemists like to build models using space filling octahedra. We will take the octahedra shapes, because mostly we will have octahedra or tetrahedra, sharing corner, sharing edges, sharing face. Like this only all solid state materials will be there. So, we use these octahedras or tetrahedras, combination of those, to build a structure, superstructure. Okay. So, I am building one like that. You see, I am taking all the octahedras, I am going to assemble them. It is like egg carton, you know, in that you place the egg, the green ones are egg, then next carton comes, in between the 4 eggs, next carton comes, then you put egg, right, like this. See, this is lithium, this fellow is so cobalt, lithium, cobalt, like the carton, egg, like that, right. No, you can nicely slip the egg. If you want, you can tilt inside and then nicely pull out. That time 2 layers has to little bit dilate, then you can pull out. Okay. Same thing we do here. Yeah. Clear? You want to see one more time? See, we have made the holder. Now we are placing egg. Now we are putting the next holder, which are pink ones are holder, right? Just for clarity, I avoided all the things, extension. Now you see the tetrahedral voids, they are all empty, tetrahedral voids are empty, because here you have only 2 types of octahedra. What is the 2 types of octahedra? You have COO6 octahedra or LiO6 octahedra. Material is done. You have LiO6 octahedra, COO6 octahedra. You combine these octahedra one after other, you built the LiCO2 structure. Very simple, na? That's all. Now, that's all. Battery chemistry is done. I don't want to get into there because time is not there. Now, all I wanted to tell you in short. Okay, let us take graphite. Graphite is a layered material, you know. I can put lithium between the layers in the van der Waals layer. The van der Waals layer I put. Let me show if I have a structure like this. I take graphite, this one or lithium, okay. In between the graphite I put lithium. So, I call it as LiC6. You can count LiC6 how? You see these atoms here, these are all face center atoms. This on the face, their contribution is 1/2. Atoms which are here, their contribution is 1/4. Atoms, so this is 1/2, one atom will come from here, one atom will come from here, 2 atoms, and then from here you will get how many atoms? How many are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 into 1/4. How much? 8 into 1/4. 2, 3, 4 atoms totally coming, right? From here 2, from the edges you get 2, totally 4 atoms, right? 4 or 6. Here also there are edge, no? So here also it is there, here also is there, here also there, here also there. So there are how many atoms here total? 2, 4, 6, 8. Then down also 8 into 1/4, 4. From these 2 you get 2, 6. So C6 Li's are in the edge center. There are 4 Li's, 1/4, 1 Li. So C6 Li. This is LiC6. So that is my anode. LiC6 is my anode, and Li1 minus X COO2 is my cathode. Okay, Li1 minus X. I can write LiC6, Li1 minus S like this. So LiCOO2, what is the oxidation state of Li? Cobalt plus LiCOO2, right? This is 4 minus, right? What is cobalt? Correct? Correct? Yes. So now let us take this material. I removed some lithium. That means I stole some egg. Correct? I stole some egg. Right? What will happen? That structure is not same as the previous structure. We can tell that as a defective structure because some atoms are missing. So, defects. I introduced a defect in the structure. Okay? So, that defect leads to some vacancy because it was Li together. I have written Li 1 minus x. That means I produced x amount of defects. This x is a fraction, right? Less than 1. So, if I remove 1 minus x, x amount of lithium out, x amount of vacancy created. If you take lithium out, the net negative charge of your lattice will increase. Correct? No? Then what you should do? You have to bring some positive charge inside. How will you bring? How will you bring positive charge inside this? What is there in your system? You have atoms. Around the atoms you have electrons. If I want to bring positive charge into my lattice, how will I bring? So, corresponding amount of cobalt I take it to 4 plus. So, I stole one electron from cobalt. Whenever I steal one lithium, one anda comes out, one electron also come out, right? You do it that way. Okay? So, what is the reaction? Yeah, this is the half cell reaction. Make sense? All of you agree? Now, where this fellow will go? Because he is coming from an electrode. This electron is also coming from the electrode. It has to be consumed. The battery means you take electron from one side, put it in the other side. So, the other side reaction is carbon plus Li plus x amount of Li plus x amount of electron produce C6LiX. Clear? C6LiX. So, I produce, this step is called in a battery, this step is called charging of the battery. Why it is charging of the battery? For this you have to spend energy. To make this compound and this compound, you have to spend energy. Put it another way, C6LiX in terms of chemical property very similar to lithium. In terms of chemical reactivity, very similar to lithium. Which is more electropositive in the world? Which metal? Lithium. Cesium. Not lithium? You go check. Which is most reactive element, lithium or cesium? Go back and check. Huh? So, that means you take cesium and lithium, put it in the table, which one will react with air first? Not lithium. Anji? Okay, to go back, find out in the electrochemical series you will find lithium is the most reactive, minus 3.5 volt, and fluorine is the most reactive again in terms of electron accepting character. So, that is plus 3.5 volt, the difference is about 7 volt. Okay, if you make a lithium and fluorine combination, that will be the highest voltage battery, 7 volt battery. Okay, fine. So, now this is a reaction during charging. Now, what will be the discharge reaction? Opposite. Okay. So, this is what is happening in your battery. Today we have studied current. So, how fast you move electron from here to here? How fast you move electron from here to here is defined by current density. In other words, what is the rate at which I form this and this? So that is the rate of the reaction, and there is a potential for each of those reaction. So you have a E cell for that. So all of them is there. Now for this reaction delta G is positive. For the reverse reaction delta G is negative. Right? And you know how where the lithium goes from the solid state. Right? So you have learnt solid state, thermodynamics, chemical kinetics, equilibrium thermodynamics, all put into one, that's called electrochemistry. Yeah, done. Yeah. Thank you.
Sir, what will be the efficiency of these lithium batteries when compared to Daniels and all the other electrochemical cells? What will be the efficiency of this when compared to that?
See, it is a tough question to answer because any cell, it's like a car for example. If someone asks what is the efficiency of the car, same petrol car of different make has different efficiency. So most of it is related to the construction. Okay. So, but if you compare lead acid battery, what you are asking? Lead acid battery to this, you cannot compare because lead acid battery has its own E cell value, lithium ion battery has its own E cell value. If you construct properly, both can be efficient. Yeah. Efficient in the sense how much energy you put, how much you get, that ratio. That can be good in both provided you construct properly.
So what is the maximum we have achieved?
350 watt hour per liter is about the capacity we achieve. 350 watt hour per liter lithium ion battery, the best ones.